In this video, we are going to learn how to solve a general trigonometric equation, linear in sine and cosine. Now, in the last video, we learned how to solve these equations when we can use a value that we knew on the unit circle in front of sine and cosine. But in this case here, in our example on the right, there's no way to divide by anything to get a known value on the unit circle that corresponds to 30, 45, or 60 degrees. So we're going to have to be more creative on finding that angle because it's going to exist somewhere in between or outside those angles now. So to do this, I'm going to solve a general one first, where I leave A, B, and C as variables, and I'll see what comes up as I look for the solution to that equation. Now, in order to solve this equation, I am going to use the sum formula for sine. So I'm going to use sine of theta plus phi is equal to sine of theta cosine of phi plus cosine of theta times sine of phi. So that's my general goal for solving this one. I want to get it into that form in some way, which means that this A value corresponds with some value for cosine, while this B value corresponds to some coordinate for sine. So what I'm going to do is go to my circle over here, and I'm going to label a general point on the unit circle over here, where I'm going to let the x value be the a value here, and the y value be b. And I'll draw a line. Now, knowing this, if I draw a reference right triangle with this particular angle I'm going to call phi, I can see here that my x side will be a length of a, and my y side will be a length of b. So now, what would the hypotenuse be? Well, we just use Pythagorean theorem. So a squared plus b squared is equal to c squared. And just take the square root of both sides, and the hypotenuse is equal to a squared plus b squared. So if I were to write what cosine of phi would be equal to with this point, it would be adjacent a over the hypotenuse, the square root of a squared plus b squared, and sine of phi would be equal to opposite b over hypotenuse, the square root of a squared plus b squared. So when I go back to my equation, I'm seeing here, if I divide by a squared, square root of a squared plus b squared, I can get a particular angle on the unit circle. So let me go write down that step. So we're going to divide by the square roots of a squared plus b squared. A very specific number. So my equation is going to look something like this. A over the square root of a squared plus b squared sine theta plus b over the square roots of a squared plus b squared cosine theta, and it's going to be equal to c over the square root of a squared plus b squared. So now I can replace these values over here with what I know they're equal to according to my unit circle. So now I will have cosine of phi, but I'll put sine of phi, the sine of theta first just to match my formula. So I'll have sine of theta times cosine of phi plus cosine of theta times sine of phi, and this will all be equal to c over the square root of a squared plus b squared. So it's really convenient here is now I can combine this into one trig function. So I'll have the sine of theta plus phi is equal to c over the square roots of a squared plus b squared. So it was a very brilliant move, and we just picked an angle and we just corresponded it to what we wanted those angles to be. So for example, if you wanted to maybe use the cosine some angle or anything like that, that you would have to think about what you want those other trig functions to be to make that happen. But I'm going to go with sine, and this is typically what you just follow the same pattern so you can get the same outcome every time. So now from here, if I wanted to solve, I would just have to take the sine inverse of this side and use my answers I get from that angle. Now, before I get to that, there's one issue that comes up. This sine theta is equal to a fraction. Now, if c is greater than the square root of a squared plus b squared, we have a problem because now we have a fraction that's greater than 1. And now sine can never equal anything greater than 1. And also, if the absolute value of c, for example, is greater than, meaning say it's negative 2 over 1, well, it wouldn't equal negative 2 either. So this becomes an issue. Because if this is true, that means that this sine theta plus phi is either greater than 1 or sine of theta plus phi is less than negative 1. This is impossible. In this case, you would have to say there is no solution. So keep in mind that this might happen. And when I work out this problem on the right, you'll see where that comes up. Now, if the absolute value of c is less than this, then we can get a solution. So what follows here is if the absolute value of c is less than that number, meaning the fraction is between negative 1 and 1. We should be able to find these answers. because then we could say that theta plus phi is equal to sine inverse of that number, c over the square roots of a squared plus b squared. And that gives us whatever this angle would be. But if you think about the solutions within a period of sine, there could also be solutions directly across on the unit circle. Over here as well at this particular angle that we might find somewhere else on the unit circle. Or if this angle yielded a negative angle, it would be directly across as well. So we have to keep that in mind, that there might be another solution, and the best way to find that particular angle is to take this angle and subtract it from pi. So the other possible solution would be theta plus phi is equal to pi minus this angle. So we can end up getting to this point. Or if it was below the x-axis, the minus would add that angle onto it, giving you the other possible solution. Now you may be wondering, now this doesn't completely solve it because I don't have theta by itself. So what I need to do is actually figure out what that phi would be so I can subtract it from both sides of the equation. And that's not hard to do because we actually have two possible ways to get phi up here. So I can figure out what the phi should be just by solving one of these equations. So if I were to just solve the bottom equation, I can get that phi is equal to sine inverse of b over the square root of a squared plus b squared. Or it could even equal the cosine inverse of a over the square root of a squared plus b squared. Either one of those would yield the angle I need to be able to subtract it and get my answer. Now let's put this into practice, what this looks like. So if I see here I have 3 sine of theta, 4 cosine of theta. Well, I'm going to find that point that where x is 3 and y is 4, which should be somewhere up here. And I would find out what the hypotenuse would be that would make that happen. So again, if I use that right triangle, I know they're overlapping now. I know this point up here is 3, 4, roughly, where x is 3 and y is 4. And if I use my Pythagorean theorem, I can find out that my hypotenuse is 5. So if I divide each side of this equation by 5, I'll get 3/5 sine of theta plus 4/5 cosine of theta is equal to 2/5. And just to put my note on the side, if I'm using phi, that means that cosine of phi should be 3/5 adjacent over hypotenuse. Sine of phi should be 4/5 opposite over hypotenuse. And now I can replace these with their corresponding trig expressions. So sine of theta, cosine of phi, phi with a line through it, plus cosine of theta, sine of phi, is equal to 2/5, giving me the expression sine of theta plus phi using that sum formula for sine, is equal to 2/5. Now from here, I can solve for this. I can get theta plus phi is equal to either sine inverse of 2/5, or as we discussed earlier, sine of theta. Sine plus phi, theta plus phi is equal to sine inverse, or pi minus sine inverse of 2/5. And then to get my final solution, I just have to subtract phi from both sides. And what that looks like would be sine inverse of 2/5 minus phi, which happens to be sine inverse of 4/5. Or on my right here, I would have theta is equal to pi minus sine inverse of 2/5 minus sine inverse of 4/5. Now I'm about to come across a problem. Possibly is that these answers need to be on this interval from 0 to pi over 2. So I need to check to see if they are, and if not, I need to make adjustments to get the correct answer. So I'm going to take my calculator, and I'll do sine inverse of 2/5 minus sine inverse of 4/5. So sine inverse of 2/5 plus sine inverse of 4/5. And I'll see here, I'll get 1.33881264. So what I can do is write that theta is equal to 1.339. That is on the interval. And then I can do my other one to be pi minus sine inverse of 2/5 minus sine inverse of 4/5. And I'll get 1.803. Both of these are on that particular interval. So now that I know that they both are on the interval, here are my two particular answers that include that little phase shift I had to deal with as well. And just to double check my mode, I am in radian mode, just to make sure. And that is how you solve a general trigonometric equation linear in sine and cosine. So I noticed a mistake I made. I see up here I put sine inverse of 2/5 plus sine inverse of 4/5 when it should have been minus. So I'm going to go back and fix that by putting minus instead. But I'm seeing here that I would not have gotten that value. I would have gotten a negative 0.516. So in order to get the correct value, I need to add 2 pi to this, a full rotation, to put it into my interval. Since I know the period of sine is 2 pi, then I'm going to add 2 pi to this, and my actual correct solution would be 5.767. So even though that is one of the angles, I'm going to use 5.767 instead. So the one note I need to make on my answer here is that I need to add 2 pi to it in order for it to be on the unit circle. And that is how you solve a general trigonometric equation linear in sine and cosine.